brief stint with functions and limits. About time we start investigating functions for their innate inherent character. In our attempt to investigate their character, we would look at some basic entities, basic indices, which would be a reflection of their character. The one that we are going to examine today falls within the jurisdiction of what's referred to as continuity. So essentially, if I have a function y equal to fx, and this is how it looks around x equal to a. This is a point P on the graph of the function corresponding to x equal to a. Now, there is a region on the graph of the function to the immediate left of P, and there is a region on the graph of the function to the immediate right of P. Now, if the graph is such that I could migrate from the immediate left of P to the immediate right of P, or vice versa. If I can migrate from the immediate left of P to the immediate right of P along the graph of the function via P, without having to raise my pen off the board, at all, then I say that the function is continuous at x equal to a. This is what it means. Continuity at a point means if I can move from a to b along the graph of the function through P, that is through x equal to a, without having to raise my pen off the board even once, then I claim continuity at x equal to a, right? What are the things that are involved during this journey? While I migrate from a to b or b to a, that means from the region to the left of P to the region to the right of P, that is x equal to a. What are the governing factors in my migration or transportation from a to b, say? Three things, essentially three things. One, the neighborhood of P to the left of A, the neighborhood of P to the right of P, right? The neighborhood to the left of P, the neighborhood to the right of P, and what is happening at P. That means the value of the function at x equal to a or lack of it. That means a neighborhood around P is important, and what is happening locally at P is important, while I determine whether I can migrate from the region to the left of P to the region to the right of P, right? So the neighborhood of x equal to a and what is happening at x equal to a, right? Unlike the notion of continuity, in which it didn't matter what was happening at x equal to a. If I had to find limit fx as x tends to a, it really didn't matter what was happening at x equal to a. Only the neighborhood was important in determining the limit of a function as x tends to a. Yes or no? Right? But this time, we give due importance to even the local behavior at x equal to a of the function, in addition to its social behavior, that is its neighborhood around x equal to a, right? So this new idea that we are going to develop and nurture today would be around not only what would happen at x equal to a, but what's transpiring in the neighborhood of x equal to a. These two together would come along to determine whether a function is continuous at x equal to a or not, right? Now, the physical meaning of continuity was, like I said, I could move from the region to the left of P to the region to the right of P without having to raise my pen off the board at all, right? But then I need to develop a proper algebraic model. I need to develop a proper algebraic model to ascertain whether a function is continuous at x equal to a or not, right? Now, in order to work out the model that leads to continuity, I would examine the complement of this problem. The complement of this problem is to examine what leads to discontinuity. That's the complement of this problem, right? What leads to discontinuity is what I'm going to examine in order to arrive at a model for continuity, right? Now, realize that if I have something like this, y equal to fx, this is x equal to a, this is x equal to a. Now, this is the point P, which is a kink, which is essentially a kink. It's not a point on the graph of the function. It's a kink. It's a kink. That means at this point the function is not, in this case, the look of the function suggests that it's not defined at x equal to a. It's not defined at x equal to a. Now, can I move from the immediate left of P to the immediate right of P along the graph of the function without having to raise my pen off the board even once? Can I do that? I can't do that. I can't do that, right? Because I can move, let's say, along this. Very close to P I could come. But suddenly at P, I would have to lift my pen off the board and jump to the region to the right of P. And therefore, there is inherent discontinuity at x equal to a. There is inherent discontinuity at x equal to a, right? So this function is discontinuous at x equal to a. What has caused this discontinuity? The fact that the function is not defined at x equal to a, right? The cause of this discontinuity is fx not defined at x equal to a. Fx not defined at x equal to a. This nature of discontinuity where you have a well-defined neighborhood, your migration to in the region to the left of P and the region to the right of P is without an impediment, not an issue. But at P there is a local issue faced. There is a local issue faced. The function is not defined at x equal to a. This kind of a discontinuity is called a missing point discontinuity. This is a missing point discontinuity. This is a missing point discontinuity. Right? For example, y equal to fx equal to sin x by x. Y equal to fx equal to sin x by xi, right? At x equal to 0, it's undefined. At x equal to 0, it's undefined. And then this is how it fluctuates, oscillates, right? In this case, f0 is undefined. However, the left hand limit at x equal to 0 is the same as right hand limit at x equal to 0 and is equal to 1. Limit fx, x tends to 0 from the greater than 0 side, the right hand limit at 0 is equal to the left hand limit at x equal to 0, and each equals 1. Each equals 1. That means limit of the function at x equal to 0 as x tends to 0 is 1. The limit exists. See, the moment the limit exists at x equal to a, you can trust the neighborhood. The neighborhood is good. It is congenial towards this migration. The moment you say limit fx x tends to a exists and is finite. Exists and is finite. It should exist and should be finite. If limit fx, in this case also, realize that at x equal to a, this length is L. Limit fx x tends to a is L. The moment L exists and is finite, we can trust what's happening in the neighborhood. What's happening in the neighborhood is good enough towards producing continuity considerations, as long as fa is well behaved. But in this case, the cause of discontinuity, this is not the cause of discontinuity. This is the way it should be. This is not the cause. This is favorable towards producing continuity. This condition is actually favorable towards producing continuity. However, the problem here is what is happening locally at x equal to a. At x equal to a, the function is undefined, and therefore in my migration from a to b, I am forced to raise my pen off the board, right? So leading to discontinuity. So if fa is undefined, then the function is discontinuous at x equal to a, and that nature of discontinuity is called a missing point discontinuity. In this case, for sin x by x, it's a missing point discontinuity. Do you realize that? It's a missing point discontinuity at x equal to 0. What is the cause of discontinuity? The fact that f0 is undefined, right? Now, let us see if the neighborhood is behaving well. When I say the neighborhood is behaving well, I mean limit fx x tends to a from the less than a side is limit fx x tends to a from the right hand a side is limit fx as x tends to a, and is some L which is a finite number. So the moment I say the neighborhood is behaving well, I'm actually implying all of this. I'm actually implying all of this when I say that the neighborhood is doing good. Now, let's say the neighborhood continues to do good. In the earlier case, in the missing point discontinuity, fa did not exist. Let us examine if fa does exist and the neighborhood is doing good, whether the function can still have discontinuity or not. Let us examine that, right? Y equal to fx this is x equal to a, this is the length L. Limit fx x tends to a is L. Limit fx x tends to a is L, right? So the neighborhood is doing good. Left hand limit at a is L, right hand limit at a is L, right? So there is no issue with the neighborhood. Now, let's say the function is defined at x equal to a. However, this is the point P on the graph of the function. For x equal to a, its value is offered by the ordinate of P, which is f of a. This is a point on the graph of the function. This represents the value of the function f of a. Right? This is a kink on the graph of the function. So this time the function is well defined at a. The neighborhood is also behaving well, yet there is discontinuity. Do you see that? Can you move from the region to the left of P to the region to the right of P? P is a point on the graph of the function without having to raise your pen off the board even once. Can you do that? You cannot. The function therefore possesses discontinuity at x equal to a, despite the neighborhood behaving properly, despite a local existence the way we want. Local existence at x equal to a is also the way we want it, yet the function has exhibited discontinuity at x equal to a. Now the reason for this discontinuity is the isolated existence of this point P, right? This is the family of the point P, but then its existence is isolated, right? P is essentially an isolated point on the graph of the function. This kind of a discontinuity is called an isolated point discontinuity. This is called an isolated point discontinuity. It's an isolated point discontinuity. Isolated point means that L is not equal to FA. Do you realize? L is not equal to FA. L is not equal to FA. If L were to be equal to FA, the function would have had continuity. Yes or no? Right? So the cause of discontinuity is L not equal to FA. The cause of discontinuity is L not equal to FA. That's the cause of discontinuity. Right? Which means two things are certain. Two things are certain. One, in order that the function has continuity at x equal to a, that means for continuity, in order that we don't have missing point discontinuity, we must make sure that FA is well defined. FA exists and is finite. Two, in order that we don't have isolated point discontinuity, we must have the left hand limit at a equal to the right hand limit at a, equal to the limit of the function at x equal to a, each is equal to f of a. This L, all of this is L, and each of them must be equal to f of a. The left hand limit at a must be equal to the right hand limit at x equal to a. Each must be equal to the value of the function at x equal to a. Yes or no? Do you all understand this? So this will prevent isolated point discontinuity, right? Very clearly then, we could have had a situation where a function does the following. A function does the following. Let's say in the neighborhood to the immediate left of A, this is what it does. At x equal to A, let's say it assumes this, and to the right of A, it does this. So this is what the function does around x equal to A. Now in this case, the function is well defined at x equal to A, say, right? But the problem in this case is that the left hand limit, which is L1, this is the left hand limit at x equal to A, L1, and this is the right hand limit at x equal to A, this is L2. That means left hand limit at x equal to A is L1 and is not equal to right hand limit at x equal to A, which is actually L2. L1 not equal to L2, that means lack of existence of limit at x equal to A. That means this is the cause of discontinuity is bad neighborhood. The cause of discontinuity is bad neighborhood in this case, right? The left hand limit is not equal to the right hand limit. The left hand neighborhood is not in sync with the right hand neighborhood, and that is what has resulted in lack of continuity. So for sure, the social aspect of continuity, the neighborhood aspect of the continuity is met if the left hand limit at A is equal to the right hand limit at x equal to A and is finite, That is what causes the neighborhood to be in good shape towards meeting continuity requirements, right? And when a discontinuity of this kind occurs, that means the left hand limit at A is not equal to the right hand limit at x equal to A, we call this abruptness. As a jump discontinuity, It's a jump discontinuity at x equal to A, right? Now, needless to say, and obviously you'll settle for this, if I had a function fx which say is sec inverse sine x. Suppose I have a function which is sec inverse sine x. Okay. At x equal to pi by 2, it's defined. Right? At x equal to pi by 2, it's defined. Sec inverse 0. Right? Sec inverse 1. Sec inverse 1, which is 0. Sec inverse 1, which is 0. Sec 0 is 1. Sec inverse 0, well defined at x equal to pi by 2, right? That means f pi by 2 is sec inverse 1, which is 0, right? But if you look at the neighborhood around x equal to pi by 2, when x is slightly greater than pi by 2, or when x is slightly less than pi by 2, when x is slightly greater than pi by 2 or x is slightly less than pi by 2, then sin x will be less than 1. Less than 1, right? And when sin x is less than 1, sec inverse of a number less than 1 does not exist. Right? So, to the right of pi by 2 and to the left of pi by 2, there is no neighborhood at all. There is no neighborhood at all. It's not even talking about left hand limit and right hand limit. There is no neighborhood at all. If there is no neighborhood, we don't even talk of a left hand or a right hand limit, right? So this is a tremendously misbehaved function in the neighborhood, right? The left hand limit and right hand limit, the concept itself does not exist because there isn't a neighborhood around x equal to pi by 2. Clear? Yes or no? Is that okay or not okay? So far so good, right? So in order that a function could be continuous at x equal to a, fa must exist and must be finite. There must be a well-defined neighborhood around x equal to a. It's not enough that the function is well-defined at x equal to a. There must be a neighborhood, no matter how small, on either side of x equal to a. 3. Limit of the function as x tends to a must exist. And it's not enough for the limit to exist. It is also important that this limit be equal to the value of the function at x equal to a, in order that there is no isolated point discontinuity. Right? Right? Say, if I have a function y equal to fx, which is box x plus box minus x. If I have a function which is y equal to fx, which is box of x plus box of minus x. Box, if you recall, is the greatest integer function less than or equal to x, right? Now, two cases. If x is an integer, it's going to be 0. If x is not an integer, it's going to be minus 1, right? So this is going to be 0 when x is an integer, and is going to be minus 1 when x is not an integer. That's a description of this function, right? The graph of this function then, let's say around x equal to y. At x equal to y, the value of the function reduces to 0. At x equal to y, the value of the function reduces to 0. Yes or no? Right? At x equal to y, the function reduces. However, when x is not I, that means in the neighborhood to the right of I or to the left of I, the value of the function is minus 1. To the immediate right of I and to the immediate left of I, the value of the function is minus 1. Yes or no? This is discontinuous at x equal to y, right? The left hand limit at I is minus 1, the right hand limit at I is minus 1, but the value of the function at I is 0. Value of the function at x equal to I is 0. So the nature of discontinuity is an isolated point discontinuity. Right? Say, if I have say the graph of y equal to fx equal to box of x, at x equal to y, box of x assumes a value equal to y. At x equal to y, box of x is I. Yes or no? To the immediate right of I, box of x will still be I. Right? At x equal to I, it assumes a value I. to the immediate right of I, it will still assume a value equal to I, right? And to the immediate left of I, it will assume a value I minus 1, right. It will assume, so this is y equal to I to the immediate right of I as well as I, and to the immediate left of I, it will assume a value I minus 1. Yes or no? Right? So which means f of I is I, the value of the function at x equal to I is I. Limit fx, x tends to I from the greater than I side, as x tends to I from the greater than I side, the value limit is I, the right hand limit is I. Left hand limit, as x tends to I from the less than I side, is I minus 1. And very clearly, therefore, limit fx, x tends to I, does not exist. There is a problem with the neighborhood. There are no local issues. There is a problem with the neighborhood around x equal to y. And do you see that there is an abruptness at x equal to y? Right? This nature of discontinuity is a jump discontinuity. It's a jump discontinuity. Right? This is a jump discontinuity in which the left hand and right hand limits are finite. Left hand and right hand limits are finite. But there could be a jump discontinuity where the left hand and right hand limits could be very large, could be infinite. That's an infinite jump discontinuity. This is a finite jump discontinuity. This is a finite jump discontinuity. We could have had an infinite jump discontinuity as well. Can I wipe this off? I'll show you. This is a finite jump discontinuity. We could have had an infinite jump discontinuity. For example, if I look at y equal to fx equal to 1 by x minus 1, say. At x equal to 1, it's undefined, right? And limit fx as x tends to 1 from the greater than 1 side. See, as x comes closer and closer to 1 from the greater than 1 side, y tends to plus infinity, right? That means as x comes closer, this is the line x equal to 1, closer and closer to 1 from the greater than 1 side, it tends to plus infinity, right? Right? And as x tends to 1 from the less than 1 side, minus infinity. Because when x is less than 1, this is negative, right? And becomes smaller and smaller, negative and smaller. So reciprocal will be negative and larger, so minus infinity. So as x tends to 1 from the greater than 1 side, it's minus infinity. Y tends to minus infinity. In fact, in this case, it has both a jump discontinuity as well as a missing point discontinuity. Because see, at x equal to 1, it's undefined. Right? And there is also a jump, and a jump of an infinite nature, right? A jump of an infinite nature. So this is both, in fact, right? Clear? Suppose So now you know. Okay, let me give you this case also. Say I have y equal to fx equal to tan inverse 1 by x. Say y equal to fx equal to tan inverse 1 by x, right? When x is not 0, y equal to fx equal to tan inverse 1 by x when x is not 0. And say it's 0 when x is 0. Suppose this is a function y equal to fx equal to tan inverse 1 by x when x is not 0 and is 0 when x is 0, right? The function is defined at x equal to 0. Its value is 0. Not an issue. The local aspect of the problem is okay in terms of the fact that it is defined at x equal to 0, right? But let me look at limit fx as x tends to 0 from the greater than 0 side. Now as x tends to 0 from the greater than 0 side, 1 by x will tend to plus infinity, right? So then this would be plus pi by 2. This is going to be plus pi by 2. Right? Similarly, limit fx as x tends to 0 from the less than 0 side. 1 by x will tend to minus infinity. So tan inverse 1 by x would tend to minus pi by 2, right? So the right hand limit and the left hand limit at x equal to 0 are not equal. The function therefore has a jump discontinuity. Clear? Suppose I had fx equal to 2 to the power tan x, and I want to examine this function at x equal to pi by 2. Suppose I want to examine this function at x equal to pi by 2. Realize that limit fx x tends to pi by 2 from the greater than pi by 2 side. What would that be? When x tends to pi by 2 from the greater than pi by 2, when x is greater than pi by 2, tan x will be negative and very large. Right? Greater than pi by 2 means second quadrant. In the second quadrant, tan x would be negative, and when you bring it closer and closer to pi by 2, it will become very large. So it will be negative and very large. 2 to the power negative of a very large number will be 0. So then this limit would be 0. The right hand limit at x equal to pi by 2 will be 0. Right? Whereas limit fx as x tends to pi by 2 from the less than pi by 2 side. When x is slightly less than pi by 2, this would be positive and very large. So this will become infinite. So in a certain sense, we say this limit is infinity. Jump discontinuity of an infinite nature. Right? Clear? Yes or no? As x tends to pi by 2 from the less than pi by 2 side, tan x becomes larger and larger and is positive. So 2 to the power larger and larger and positive would be larger and larger and positive, isn't it? No? Limit 2 to the power tan x as x tends to pi by 2 from the less than pi by 2. When x is less than pi by 2, tan x is in the first quadrant, right? Tan x will be positive and will become larger and larger, 2 to the power larger and larger. This will be larger and larger. So plus infinity. Right? say I had a function fx which is mod sin x by x when x is not 0. When x is not 0 means now this is the description of the function in the neighborhood of x equal to 0. In the neighborhood of x equal to 0, this is how the function is defined, and is equal to 1 when x is 0, and is equal to 1 say when x is 0. So the function is defined at x equal to 0 and is equal to 1. Alright. Now I want to examine the function at x equal to 0. I want to examine the function at x equal to 0. Now let me find limit fx, x tends to 0 from the greater than 0 side. When x is slightly greater than 0, sin x will be positive, mod sin x will be sin x. And this will be 1, right? Similarly, limit fx, x tends to 0 from the less than 0 side. When x is slightly less than 0, sin x will be negative, mod sin x will be minus sin x. Sin x by x as x tends to 0 would be 1, so this will be minus 1. So left hand limit and right hand limits are not equal, and they are not equal to the value of the function at x equal to 0. The nature of discontinuity is a jump discontinuity. This is a jump discontinuity. Right? If I had, yes.
Won't this be also minus x? So
No. Why should that be minus x? No, but it's mod sin x. This x is not under modulus. If it was mod sin x by mod x, then when x tends to 0 from the less than 0 side, mod x would have been minus x. But x is outside the modulus, see? Mod sin x by x. So x will remain x. Whether x is to the right of 0 or to the left of 0, x will remain x. If it was mod x, then to the right of 0, mod x would have been x. To the left of 0, mod x would have been minus x. But this is only x. Mod is only in the sin x. Got me? So far so good, right? Now say if I have a function y equal to fx, and it goes as 2x plus 1 for x less than 0, say. And it goes as x minus 1 for x greater than or equal to 0. Suppose this is a function y equal to fx, which is 2x plus 1 for x less than 0 and is x minus 1 for x greater than or equal to 0. And one wants to examine the continuity of this function. One wishes to examine the continuity of this function. Now, realize that to the right of 0, it goes as y equal to mx plus c, a straight line with slope 1 and y-intercept minus 1. At x equal to 0, its value is minus 1, right? This is the description of this function to the right of x equal to 0. Right? To the left of x equal to 0, it goes as a straight line mx plus c. Right? Right? Y-intercept 1 and slope 2. Right? To the left of 0. So, at x equal to 0, let me make it steeper because it has more slope than this. So I'll make it steeper. Do you realize this? The left hand limit at x equal to 0 is 1. The right hand limit at 0 is minus 1. The value of the function at x equal to 0 is minus 1, right? In this entire description of the function, see, there are times when they'll say examine the function for continuity. If it's an open-ended statement, then you would examine the function for continuity at those points where it proposes to change behavior. Where there is a proposed change of behavior, that's the point you would want to examine the function for continuity. In this case, this function changes behavior at x equal to 0. That for sure would be a point of contention towards examining the function for continuity. So at x equal to 0, I find that the function is discontinuous, right? The nature of discontinuity is a jump discontinuity, right? Yes or no? Right? At all other points, do you see that the function is continuous? If I look at any other point P on the graph of this function, then I can move from the immediate left of P to the immediate right of P without having to raise my pen off the board. Or look at any other point P here, then I could move from the left of P to the right of P without having to raise my pen off the board. So this function is continuous everywhere except x equal to 0, where it exhibits a jump discontinuity. A jump discontinuity is what it exhibits. Clear? Suppose I had x plus a, and someone said find a so that the function is rendered continuous at x equal to 0. Find a so that the function is continuous at x equal to 0, right? Now, in order that this function be continuous at x equal to 0, the left hand limit at x equal to 0, which is given by this description, will be equal to the right hand limit at x equal to 0, which is given by this description. Yes or no? So, to be continuous at x equal to 0, limit fx, x tends to 0 from the greater than 0 side. Now, when x is slightly greater than 0, this is the description of the function x plus a, which is like limit x plus a, x tends to 0 from the greater than 0 side, which is a, and that must be equal to, that in turn must be equal to limit fx, x tends to 0 from the less than a side, less than 0 side, which means limit 2x plus 1, x tends to 0 from the less than 0 side is 1, right? Which clearly gives me a equal to 1. So if a is made equal to 1, then the function is rendered continuous at x equal to 0, right? So if you have to examine a function for continuity or otherwise, then examine those points. Of course, in addition to wherever the function is undefined, those are obvious points. But if the function proposes certain change of behavior, then those certainly are points to be examined for continuity or otherwise. Yes or no? and doesn't mean that a function changes behavior. The function has to be discontinuous. Not necessarily. For example, if you look at the graph of y equal to fx equal to mod x. Y equal to fx equal to mod x. Right. So it goes as y equal to x to the right of 0. It goes as y equal to minus x to the left of 0. So the behavior to the left of 0 is commensurate with y equal to minus x. To the right of 0, it's commensurate with y equal to x. Therefore, there is a change of behavior at x equal to 0. But as you can see, as x tends to 0 from the less than 0 side, fx tends to 0. As x tends to 0 from the greater than 0 side, fx tends to 0. Right? That means limit mod x tends to 0 from the less than 0 side is like limit minus x tends to 0 from the less than 0 side, which is 0. And limit mod x tends to 0 from the greater than 0 side to the right of 0, mod x goes as x tends to 0 from the greater than 0 side, and this is 0. So despite a change of behavior proposed at x equal to 0, the function does not exhibit discontinuity at x equal to 0. The value of the function is also 0 at x equal to 0. Yes or no? Sounds all right? So all that I'm saying is, if there is a change of behavior that you perceive in a function at x equal to a, then certainly investigate the function at that point. You can be suspicious about what is happening at x equal to a. Whether or not your suspicion goes true is another issue, but then you must check the function for continuity or otherwise at that particular point. Clear? Yeah. Why not? I mean, he's saying, can a function be discontinuous at more than one point? Yes, it can be discontinuous at any number of points. Say, in a given interval, a function is like this: missing point, isolated point, jump discontinuity. See, in this interval, a to b, this function is discontinuous at this point. Yes or no? At x equal to, say, a naught, it's discontinuous, missing point discontinuity. At this point, this is a point on the graph of the function, say a1, it has an isolated point discontinuity. At this point, say x equal to a2, it has a jump discontinuity, and I can put the point P on the graph of the function, jump as well as isolated point. Why not? Yes, you have a question, please ask. Sorry? A quadratic expression is continuous everywhere. I'll tell you why. Very simple. In fact, a quadratic does not change behavior anywhere. See, y equal to fx equal, suppose a is positive, ax squared plus bx plus c. If it has real roots, it will be like this. If it has coincident roots, it will be like this. If it has no real roots, it will be like this. Do you see that it's actually continuous everywhere? I mean, you look at this point, for example, alpha, the left hand limit is 0, the right hand limit is 0 at alpha, the function has a value equal to 0 at alpha. Same with beta, the left hand limit is 0, the right hand limit is 0 at beta, the value of the function is 0 at beta. At any other point P, you can move from the left of P to the right of P without having to raise your pen off the board even once. A quadratic expression is continuous no matter what, always. At all real values of x, it is indeed continuous. Right? A linear expression, y equal to fx equal to, say, ax plus b, is a straight line, and again it is continuous for all real values of x. right? A linear expression, y equal to a linear expression, a linear function will be continuous. A quadratic function will be continuous. A constant function, y equal to fx equal to some constant c. This is continuous for all x. Y equal to c is continuous for all x, right? So far so good, right? Somebody asked a question? No? I'll come to that. Give me a few minutes. Yes, the answer is yes. Why so? I'll explain. Any polynomial will be continuous for all real x. All trigonometric functions will be continuous in their domain. Exponential will be continuous in its domain. Logarithm will be continuous in its domain. I'll just come to that. Let me build it up for you completely, right? Now, obviously, like I told you, y equal to box x is discontinuous every time x is an integer. Every time x is an integer. Similarly, y x equal to fractional part of x equal to fractional part of x is also discontinuous every time x is an integer. Realize that this is how it goes. This is the graph of y equal to fractional part of x. If you look at, say, x equal to 2, an integer, right? Limit fractional part of x as x tends to 2 from the less than 2 side. As x comes closer and closer and closer to 2 from the less than 2 side, fractional part of x comes closer and closer to 1. So the left hand limit at 2 is 1. Limit fractional part of x, x tends to 2 from the greater than 2 side. As x comes closer and closer to 2 from the greater than 2 side, you realize that fractional part of x comes closer and closer to 0. So the right hand limit at x equal to 2 is 0. The left hand limit is 1. So at any integer, whether it is 0, plus minus 1, plus minus 2, fractional part of x will be discontinuous for all x belonging to the set of integers. However, when x is not an integer, look at an x which is not an integer. Look at this point P. It is continuous. So fractional part of x and box x both have this common property. They would be discontinuous every time x is an integer. The nature of discontinuity would be a jump discontinuity, but they will be continuous every time x is not an integer. Both fractional part of x and box x are discontinuous every time x is an integer, but are continuous every time x is not an integer. That is important to understand. The nature of the discontinuity exhibited by both is jump discontinuity, right? In both cases, there is a problem with the neighborhood. Left hand limit is not equal to the right hand limit at x equal to an integer, right? So far so good, right? Not a problem. Now, see, I had a classification that I imparted to you for discontinuity. discontinuity had a classification like a missing point discontinuity and isolated point discontinuity, right? In both missing point discontinuity and isolated point discontinuity, at least in the missing point discontinuity for sure, there was no problem with the neighborhood, right? And then we had a jump discontinuity, which essentially had a problem with the neighborhood. There is yet another classification for discontinuity. See, continuity does not get classified. Discontinuity gets classified, right? Good people would be of one kind, evil would be of many kinds, right? So look upon discontinuity as evil, as devilish, right? It can be classified. Bad and very bad, severe and very severe. Good people are of the same kind. I mean, it's like good and very good would be looked upon as the same, but bad and very bad, right, is a different thing. So discontinuity has yet another classification. See, in a situation of this kind, say in a situation of this kind, say at x equal to a, it's a discontinuous function at x equal to a, right? And the nature of discontinuity is a missing point discontinuity. It's a missing point discontinuity at x equal to a, right? There is no problem with the neighborhood. Now this function could be modified to another function. This function could be modified to another function in which all that I do is I redefine this function at x equal to a. Now this is a function which has L as its limit at x equal to a. L is limit fx as x tends to a. The neighborhood is in good place, right? Even this function, an isolated point discontinuity with no jump, an isolated point discontinuity with no jump, an isolated point discontinuity with no jump. This is an isolated point discontinuity. In both these cases, they share one common feature. Both have L as a finite number, which is the limit fx as x tends to a, both from the greater than a side as well as less than a side, right? So now the issue, the factor that caused discontinuity of both these functions was their description locally at x equal to a. There was a local issue that initiated a discontinuity of this function at x equal to a, right? There was a local problem. There was no problem in the neighborhood. Now, suppose in both these cases, for both these cases, I define another function. Let me look at them like this, say similar stuff, but in the neighborhood of x equal to a. Say I define a function y equal to fx, y equal to phi x, a new function y equal to phi x, a new function which is the same as fx when x is not a. When x is not a, phi x is the same as fx. That means in the neighborhood of x equal to a, the new function phi x is identical to fx. In the neighborhood of x equal to a, the new function phi x is the same as fx. But at x equal to a, it says I'm not going to behave like the mother function. It says at x equal to a, phi x says I'm going to assume a value equal to this L. I'm going to assume a value equal to this L. This is the new function, which is the same as fx, in the neighborhood of x equal to a. That means when x is not a, but at x equal to a, it says I'm going to assume a value equal to L. For sure, phi x is not identical to fx. Phi x is identical to fx only in the neighborhood of x equal to a. But at a, it says I'm not going to inherit the character of fx. In this case, the character of fx at x equal to a is that it's undefined. In this case, the character of fx is at x equal to a, that it's isolated point at x equal to a. It's not equal to L. Right? So this function phi x says I'm going to be little more practical. The good things about fx, that is its neighborhood, I'm going to embrace, whereas as far as what was happening to fx at x equal to a, I'm not going to take notice of. I'm going to assume a value equal to L at x equal to a. This is the new function. So phi x is produced, this function phi x is produced by a local modification of fx, right? If it's produced by out of a local modification of fx, then the graph of phi x will be the same as fx at around x equal to a. It's going to be the same as fx. In addition, at x equal to a, it will assume a value equal to L. L will also be equal to f of a. L will be equal to the value of the function at x equal to a. That means phi of a. This is the value of the function at x equal to a. Right? So phi x is produced only by a local modification of fx, in which I have forced the value of phi x at x equal to a to be L. And I have not tampered with the neighborhood of fx in my bid to create phi x. Then this phi x is a continuous function at x equal to a. This phi x created simply out of a local modification, local change of fx at x equal to a is continuous at x equal to a. Whereas fx was discontinuous at x equal to a, be it this case or be it this case. Fx was discontinuous at x equal to a, but a local change in fx could produce a new function which is continuous at x equal to a. Right? So this kind of a discontinuity where the neighborhood is not a problem, this kind of a discontinuity where the neighborhood is not a problem is called a removable discontinuity. This kind, it's a discontinuity, be it this or this. Both these cases belong to a category called removable discontinuity. It's a removable discontinuity at x equal to a. Yes. If a function has a well-behaved neighborhood, that means the left-hand limit is equal to the right-hand limit at x equal to a, but it only has a local problem. That means either it's not defined at x equal to a, or if it's defined, its value is not equal to the limit of the function at x equal to a. Then, just by merely instigating a local change at x equal to a, I can develop a new function phi x which is continuous at x equal to a. Then this function fx is discontinuous, is still evil, but of a less severe kind, and it's called removable discontinuity. I'm permitting only a local change to create this modified function phi x. Don't think that phi x is fx. Phi x is different from fx because it's different at least one point, so it would be looked upon as a different function. But it's continuous at x equal to a, and it's obtained out of a function which is discontinuous but is known to have a removable discontinuity. It has a removable discontinuity. Yes or no? Right? In contrast, so for example, for example, say I have y equal to fx, which is x squared minus a squared by x minus a, right? So this is a function y equal to fx is x squared minus a squared by x minus a. Very clearly, this is x plus a when x is not equal to a. When x is not equal to a, it's equal to x plus a, right? But is undefined at x equal to a. Do you realize it's undefined at x equal to a? But as long as x is not a, its value will be x plus a. Yes or no? Right? That means it will go along a straight line y equal to mx plus c. This is x equal to a. This point is 0a. At x equal to a, it's undefined. It is undefined. Huh?
But writing fx equal to x plus a and x minus a square by x minus a is equivalent also.
Is it? Is it equal to x plus a always? No. It is x plus a as long as x is not equal to a. No. No. Just look at this function. Don't think of any value. Think of this function x squared minus a squared by x minus a. You can write this as x minus a into x plus a by x minus a. But when you cancel x minus a, cancelling is like dividing by x minus a, isn't it? That means dividing by 0 if x is a, which is not a permissible operation, right? It's x minus a, as this cancellation can take place if x is not a. But will not take place when x is a, because if you cancel when x is a, that means you are giving legality to division by 0. Not allowed, right? So it's undefined for sure at x equal to a, right? Now, so it has a missing point discontinuity at x equal to a. But the limit fx as x tends to a is 2a. Yes or no? Because when you take the limit, you are not bothered what's happening locally at x equal to a. You are only bothered about the neighborhood of x equal to a, which is given by x plus a. Limit fx as x tends to a will be 2a. Then you bother only about this line of description, because this line of description is in sync with the neighborhood of x equal to a, right? And this is only the limit of the function. It has a missing point discontinuity, right? The left hand limit at a is equal to the right hand limit at a and is equal to 2a. There is no issue with the neighborhood, right? But I could define a new function, say phi x. I could define a new function, say phi x, which is x squared minus a squared by x minus a when x is not a, and is right and is equal to 2a when x is a. I could define this new function. That means in the neighborhood of x equal to a, this function is the same as fx. But at x equal to a, it says I'm going to stay free from fx. I'm going to define myself as 2a at x equal to a. Because at x equal to a, fx has a problem. So phi x says I'm not going to behave like fx when x turns out to be a. For the neighborhood of x equal to a, it's okay for me to behave like fx. Right? So then, this newly defined function with a modification at x equal to a will have a graph like this. Phi x at x equal to a, it assumes a value 2a. It's going to be the same as fx, except that x equal to 2a, where fx had a kink. This will be the value of this will then turn out to be a point on the graph of phi x. So phi x will turn out to be like this, where at x equal to a, it has a value equal to 2a. Yes or no? So this function phi x, fx is discontinuous at x equal to a, but the nature of discontinuity is a removable discontinuity. It has a removable discontinuity. Fx has a removable discontinuity at x equal to a. Yes or no? Right? You have a question? No? Say if I have a function y equal to fx, which is sin x by x, right? Like I told you so many times, this would be the graph of the function. At x equal to 0, it's undefined, but limit fx as x tends to 0 is 1. So neighborhood is not a problem in this function. What is the problem? Locality. X equal to 0, the locality is a problem for the function, right? If it's a problem only at x equal to 0, which is resulting in discontinuity, then the nature of discontinuity would be looked upon as removable discontinuity. Removable discontinuity at x equal to 0. And I could define a new function phi x, which is the same as fx when x is not 0, but is equal to 1 when x is 0. So only a local change initiated in fx to create this new phi x. In the neighborhood of x equal to 0, it's the same as fx. But when x is 0, it behaves as 1. Then what would be the graph of phi x? The graph of phi x versus x is going to be, now there won't be any kink, no missing point. Is continuous at x equal to 0. It is continuous at x equal to 0. Yes or no? So it has a removable discontinuity, one of a less severe kind. It is not as severe a discontinuity as one would hope. Clear? I'll tell you severe discontinuity also. That is where I'm coming to. What will make it very severe is what I'm going to now discuss. Right now, why do we? No, we are not removing. Fx will remain fx. I'm not saying that fx will change. I can create a new function phi x which will be continuous only by bringing about a local change. It will not mean that fx will suddenly become continuous. A new function created out of a template of fx in the neighborhood of fx, but only by redefining fx at x equal to a is continuous. Yes, you have a question. No, that will be non-removable, which would be severe because it doesn't have a good neighborhood. Left hand limit is -1, right hand limit is +1. So there is going to be a problem. It will not be a removable discontinuity. Okay, I'll discuss that. Now, a function in contrast, something like a jump discontinuity. A discontinuity of this kind, say for example, can you do anything to the function at x equal to a to restore continuity? Nothing can be done. And playing around with the neighborhood is not only dangerous, it is unacceptable. Right? You know that? So, if you have to make amends, if you have to make changes, then you make them only in-house. You don't extend your wings to the person next door and tell her you're not wearing the right hair clip. Okay? So which means socially, so the entire concept of calculus, like I said, is a genuinely social concept. You know, the rules and cardinality of social behavior get completely embodied within the philosophy of calculus, and therefore, you know, to say that you're allowed only local changes, you're not allowed changes in the neighborhood, is pretty much within the purview of our social rules. Social behavior might be different, but social rules are these, right? So then, in this case, at x equal to a, can you do anything to the function at x equal to a? Either define or redefine. Anything at x equal to a can you do without tampering the neighborhood to restore continuity in this? Nothing can be done. Nothing can be done at x equal to a to bring about continuity at x equal to a. Yes or no? Right? So, this function is beyond remedy, is beyond repair, right? The discontinuity that you see here is beyond repair until and unless you are antisocial. Perforce you pull this down and make it coincide with this, which is not acceptable, right? So we will go by the rules of the civilized society, which does not permit this. So then, in this case, the discontinuity is one where a local change cannot bring about continuity, right? Why? And the cause is that the left hand limit at x equal to a, L1, is not equal to the right hand limit at x equal to a, which is L2. So if limit fx, x tends to a from the less than a side, is not equal to limit fx, x tends to a from the greater than a side, then the nature of discontinuity is a non-removable discontinuity. It's a non-removable discontinuity. It's a non-removable discontinuity at x equal to a. Then anyways, so if you have something like this, say at x equal to a, say both tend to plus infinity, then also it is non-removable. This also is a jump discontinuity of an infinite kind.
But at x equal to a also it's infinite.
Yeah, but infinite is not a value. Is not a value, right? So this, can you do anything to the function to bring about continuity at x equal to a? Nothing. In this case, think of it physically. Nothing can be done to this function at x equal to a to bring about continuity, right? So this also is non-removable discontinuity. He's saying left hand limit at a is plus infinity, right hand limit at a is plus infinity. Plus infinity means limit will exist only if it is finite. So plus infinity is only a notion that I'm suggesting that it becomes larger and larger at a. But the limit, neither the left hand limit is finite nor the right hand limit is finite. The function will have a non-removable discontinuity at x equal to a. Okay, suppose a function has no neighborhood at a certain point. That means, say, Chinese mustache. Okay, Chinese mustache means one small hair in the middle and nothing on either side. Right? At x equal to a, it's well defined. And now the thing is, the limit at x equal to a does not exist. Because there is no neighborhood. Now you're not going to create a neighborhood, go out and do things to create a neighborhood, right? Right, Siddharth? So, that if you can't modify the neighborhood, how can you go and create neighborhood? Right? That means in order to define that function, you will have to create neighborhood. Are you allowed to create neighborhood? Is that considered consistent moral behavior? No, right? Chinese discontinuity. No neighborhood. I do not know if there is a name for this. You will have to Google and find a name for this discontinuity. It's not known to me. But for the sake of good casual conversation in the class, we can refer to this as Chinese discontinuity. Don't quote me anywhere for this. Okay. Right? So this is a non-removable discontinuity because local changes cannot remedy discontinuity here. Because left hand limit is not equal to the right hand limit at x equal to a. So far so good, right? Say for example, like Shans you said, y equal to fx, say mod x by x, mod sin x by x. This function limit fx, x tends to 0 from the greater than 0 side would be like I told you, mod sin x will be sin x by x, x tends to 0 from the greater than 0 side would be plus 1, limit fx, x tends to 0 from the less than 0 side, fx would be mod sin x would be minus sin x by x, x tends to 0 from the less than 0 side is minus 1. So the neighborhood itself is so misbehaved. Left hand limit at x equal to 0 is not equal to the right hand limit at x equal to 0. There is no question of doing anything at x equal to 0 that would salvage pride in this function. That means restore continuity, right? Nothing can be done at x equal to 0 to bring about continuity of this function. So the nature of discontinuity is very severe and would be looked upon as a non-removable discontinuity at x equal to 0. It's a non-removable discontinuity at x equal to 0. Causes that the right hand limit at 0 is not equal to the left hand limit at x equal to 0, right? So far so good, right? Say, if I had box x, fx equal to, say, box x by x, right? And let me look at x equal to 2, say. Let me look at x equal to 2, an integer. Because box x changes behavior every time x is an integer, right? Now, limit box x by x, limit of this function as x tends to 2 from the less than 2 side. When x is slightly less than 2, box x will be identically equal to 1, right? So this will become 1 by 2, yes or no? That's a left hand limit at x equal to 2. Limit box x by x, x tends to 2 from the greater than 2 side. When x is slightly greater than 2, box x will be identically 2. So 2 by 2, that makes it 1. So the left hand limit at 2 is not equal to the right hand limit at 2. The nature of discontinuity would be non-removable jump, and of course also non-removable discontinuity. A jump discontinuity will always be non-removable. Right? Seems good?
Jump discontinuity is always non-removable, but non-removable discontinuity, will it be always jump?
Non-removable discontinuity has to be jump because the left hand limit will not be equal to the right hand limit. So it has to be jump. Right? Can be? Not always, not always. See, like I said, isolated point discontinuity again can be of this kind. See, say there is an isolated point of this kind. This is an isolated point P at x equal to a. This is removable because left hand limit is equal to the right hand limit. But so this is removable isolated point discontinuity because the neighborhood is in good shape. Whereas this is the point P on the graph of the function at x equal to a. This is also an isolated point discontinuity, but also jump. And this is non-removable. So this is an isolated point discontinuity which cannot be removed. This is an isolated point discontinuity that can be removed. Right? Yeah. So for each point, horses for courses, for each point we'll have a new description for their discontinuity. So I'm talking of discontinuity at x equal to a. For different points, I'll talk of discontinuities independently. Right? Clear? So if there are a number of points, I will have to address each point and the nature of discontinuity at those points independently. Right? Now, say there is a function defined over a finite interval. Say there is a function that is defined over a finite interval. X equal to a. This is a function defined over an interval that is x belongs to a to b. I hope you understand the meaning of these brackets. Square means it will include A. If it was a round bracket, means it will not include A. Right? Now, see, suppose I didn't have knowledge of this function to the left of A and to the right of B. Suppose there was no data available on this function to the left of A and to the right of B. These are the endpoints of the interval. These are the endpoints of the interval. X equal to A and X equal to B. Now, we will be less harsh with the endpoints A and B in as far as suggesting continuity or otherwise at A and B. In the sense, when I talk of continuity at X equal to A, the left end of the interval, X equal to A is the left end of the interval. X equal to A is the left end of the interval. Right? And then I talk of limit fx. At A, I talk of limit fx, x tends to A from the greater than A side. As x comes closer and closer to A from the region to the right of A, which is the right hand limit at x equal to A, which is the right hand limit at x equal to A. This is equal to f of A. If the right hand limit is equal to f of A, then we say the function is right hand continuous at x equal to A. The function is right hand continuous at x equal to A. As far as B is concerned, I can approach B only from the region to the left of B, right? And this is FB. Now, for the right end x equal to B, we talk of limit fx, x tends to B from the greater than B side. If this is equal to FB, then the function is said to be right hand continuous, left hand continuous at x equal to B. X tends to be from the less than B side, beg your pardon. X tends to be from the less than B side. X tends to be from the less than B side is FB. Then the function is said to be left hand continuous at x equal to B. Left hand continuous at x equal to B. This is what. So now, for the endpoints of the interval, we say the function is, for this end we talk of right hand continuity, for this end we talk of left hand continuity, right? So that's the little bit of relaxation that we make to the endpoints of the interval, right? Now, a function is said to be continuous in an interval. A function is said to be continuous in an interval if it is continuous at all points of that interval. A function is said to be continuous in an interval if it is continuous at all points of that interval. If there is an x in the meat of the interval, then we say limit fx as x tends to this x from the less than this side or right hand limit must be equal to the value of the function, right? But for the endpoints of the interval, we talk of left hand continuity, right hand continuity and left hand continuity. But for all points in the meat of the interval, we describe continuity the way we described in terms of neighborhood on either side. So a function that is said to be continuous in an interval is continuous at all points of that interval, with the left hand of the interval and the left end of the interval and the right end of the interval slightly relaxed in terms of their continuity requirements. Got me? We define continuity at x equal to A as limit fx x tends to A from the greater than A side as fa. That's a new definition of continuity for the endpoints of the interval. That's all. Fa must exist and should be finite. Fb must exist, should be finite. Right? So far so good, right? Now another way, cosmetic representation of continuity at x equal to a. See, what I told you was, 1, for continuity at x equal to a, fa must exist and be finite. Right? 2, limit fx x tends to a from the less than a side must be limit fx x tends to a from the greater than a side. Both must be finite and must be equal to the value of the function at x equal to a. That is limit fx. These two statements, if these two are equal, then they are written as one consolidated statement. Limit fx x tends to a equal to fa. In fact, this one single statement says everything. First of all, if this limit exists and is finite, that means the left hand limit is equal to the right hand limit and is finite and is equal to the value of the function. That means fa also exists and is finite. So this, and the moment you are able to take a limit, that means there is also a neighborhood around x equal to a. So this then is really the summary of continuity at x equal to a. It says everything. Right? Sometimes this statement is rewritten. It's rewritten as, if I took, say, x equal to a plus h. If I took x equal to a plus h. Clear? Then, as x tends to a from the greater than a side, when x is slightly greater than a, h tends to 0 from the greater than 0 side, yes or no? Because if x is greater than a, h will be greater than 0. H will be greater than 0. Will tend to 0 from the greater than 0 side, yes or no? Right? Similarly, as x tends to a from the less than a side, then x minus a will be negative. That means h will be negative and will come closer and closer to 0. So h then tends to 0 from the less than 0 side. Yes or no? Right? So now this statement is written as limit, put x equal to a plus h. I go to the h domain then. F of plus h tends to 0 from the greater than 0 side. That will be the right hand limit at x equal to a, because if h tends to 0 from the greater than 0 side, x tends to a from the greater than a side. So this is the right hand limit at x equal to a, right? And limit f of a, h tends to 0 from the less than 0 side. This is my x. If h is less than 0, this will be less than a. If h is less than 0, this will be less than a. So this is the left hand limit at x equal to a. This is the right hand limit at x equal to a. And both must be equal. Both must be equal for continuity. Not just the two of them being equal. They must in turn be equal to the value of the function at x equal to a. They in turn must be equal to the value of the function at x equal to a. The left hand limit at x equal, this is the right hand limit at x equal to a. This is the left hand limit at x equal to a. Both must be equal, finite, and must be finitely equal to the value of the function at x equal to a, that is f of a. Yes or no? All's good? Now, so this statement is combined, these two statements are combined as one single statement. Limit for continuity at x equal to a, limit f of a plus h tends to 0 equal to f of a. F of a plus h tends to 0 must be equal to f of a. So instead of saying limit fx x tends to a is f of a, we could have also said limit f of a plus h tends to 0 is f of a. H tends to 0 from the greater than 0 side will give me the right hand limit at a. H tends to 0 from the less than 0 side will give me the left hand limit at x equal to a. Yes or no? Right? say for example, there is a function fx which has a certain property. Say a function defined from R to R, real numbers to real numbers, domain real numbers, codomain also real numbers, and that function fx has a property that for all x and y belonging to the set of real numbers, f of x plus y is fx into fy. F of x plus y is fx into fy, say. Right? Clear? And it is given that fx is continuous at x equal to 0. It is given that fx is continuous at x equal to 0. Right? Check if fx is continuous for any x equal to a. That means for all x. Check if fx is continuous for any x equal to a, say. Alright. Now, first of all, if fx is continuous at x equal to 0, what does it mean? It means limit fx, x tends to 0 must be equal to f0. This is what it means. Continuity at x equal to 0 reduces to this condition. Right? Now, let me find f0. This is an identity. This is true for all xy. This is a property of this function, true for all real xy. Right? Now in this, since it's true for all xy, let me put y equal to 0 on both sides. Let me put y equal to 0 on both sides. Then I end up getting fx equal to f of x into f of 0. Right? So this gives me f of 0 equal to 1. This gives me f of 0 equal to 1. Yes or no? So this limit fx x tends to 0 for this function turns out to be f0, which is 1. Right? Now, let me check the function for continuity at x equal to a. Now, if I can establish limit f of a plus h as h tends to 0 equal to fa, then the function will be continuous at x equal to a. If this can be proved to be equal to fa, then the function would be continuous at x equal to a. Yes or no? Right? Now this is limit f of a plus h. See, f of a plus h is going to be f of a into f of h. That's a property of this given function. Right? So this is going to be f of a into f of h as h tends to 0. Yes or no? Right? F of a will wriggle out of the limit. F of a will wriggle out of the limit. Yes or no? Limit fh h tends to 0. Hey, limit f of something as something tends to 0 is 1. Limit f of something as something tends to 0 would be 1. So this would be 1 and this would be fa. So limit f of a plus h as h tends to 0 turns out to be fa, and fx therefore is continuous at x equal to a. That means it's for any a, that means it's continuous for all real x. This function, if it's continuous at x equal to 0, will be continuous for any other real x. Will be continuous for any other real x. Right? Got me? All's fine so far? Now, let me look at some very rudimentary properties of continuous functions. Very basic rudimentary properties of continuous functions, right? If fx is continuous at x equal to a, then lambda fx, where lambda is any real constant, lambda fx will also be continuous at x equal to a. If fx is continuous at x equal to a constant times fx will also be continuous at x equal to a. That means 2 times fx will be continuous, minus 3 times fx will be continuous, half of fx will be continuous at x equal to a. Very simple to see that. See, if fx is continuous at x equal to a, it means limit fx, x tends to a must be equal to fa. This is what it means. Limit fx, x tends to a must be equal to fa if f is continuous at x equal to a, right? Yes or no? Now, let me look at this phi x, which is lambda fx. I want to show that phi x is also continuous at x equal to a. Now, limit phi x as x tends to a. If this I can show is phi a, then the function phi would be continuous at x equal to a. So, this is like limit lambda fx as x tends to a. Lambda will come out. Limit fx as x tends to a, which is lambda fa, right? Hey, but lambda fa is phi a. Lambda fa is phi a, yes or no? Which means if fx is continuous at x equal to a, phi, which is lambda times fx, will also be continuous at x equal to a. Why? Because limit phi x as x tends to a turns out to be phi a, right? Got me? In fact, can I wipe this off? However, if fx is discontinuous at x equal to a, lambda fx will also be discontinuous provided lambda is not 0. Provided lambda is not 0. If lambda is 0, it will become a constant function and then it will be continuous for all x. But if lambda is not 0 and if fx is found to be discontinuous at x equal to a, lambda times fx will also be discontinuous at x equal to a. In fact, see, box x is discontinuous, say at x equal to an integer. 3 times box x will also be discontinuous. Minus box x will also be discontinuous, and so on and so forth, right? So, product for sure, product of two discontinuous lambda times a continuous function will always be a continuous function, all right? Similarly, if fx is continuous at x equal to a, then lambda 1 times fx plus lambda 2 will also be continuous at x equal to a. Will also be continuous at x equal to a. However, if fx is discontinuous, lambda 1 turns out to be 0, then this will be continuous. But if lambda 1 is not 0, then lambda 1 times a discontinuous function plus lambda 2 will also be a discontinuous function. Right? If fx is continuous, for sure, lambda 1 fx plus lambda 2 will always be a continuous function. Right? If fx is continuous at x equal to a, and gx is also continuous at x equal to a, then let me tell you, fx plus minus gx will also be continuous at x equal to a. That means sum or difference of two continuous functions will be a continuous function. Sum or difference of two continuous functions will be a continuous function at a certain point. Say, if I have, say, so this means what? This means limit fx, x tends to a equal to fa, because f is continuous at x equal to a. This means limit gx, x tends to a equal to ga. Why? Because gx is continuous at x equal to a. Then let me look at phi x, which is fx plus gx, where fa and ga have to be finite numbers, right? Then limit phi x, as x tends to a, would be limit fx plus gx as x tends to a. Limit of a sum will be sum of the limits. But this is fa because f is continuous at x equal to a. This is ga because g is continuous at x equal to a. So this then turns out to be fa plus ga. That means fa plus ga is phi a, That means phi then is continuous at x equal to a. So similarly, if you take the difference, you will get the same thing. Sum or difference of two continuous functions will be a continuous function, right? Give me some time, I'll tell you. However, sum of two discontinuous functions need not be a discontinuous function. It may be discontinuous, it may be continuous. In the sense, say y equal to fx is box x is discontinuous at x equal to an integer. Y equal to gx is minus box x is discontinuous when x is an integer. Look at their sum. Their sum is 0, which is a continuous function. So sum of difference of two discontinuous functions may be continuous, may be discontinuous. In this case, see, this is discontinuous, this is discontinuous, but their sum is continuous. It's a function, right? So sum or difference of two discontinuous functions may be continuous, may be discontinuous. Clear? I'll, I'll, if I fail to explain this to you by the time I've finished, raise your query. Okay, I'll explain that also. So one is continuous, other one is discontinuous, say. Right? Say fx is continuous at x equal to a, and gx is discontinuous at x equal to a. Then I claim that sum of a continuous and discontinuous function will be a discontinuous function. This will be discontinuous at x equal to a. Sum of a continuous and discontinuous function will be discontinuous at x equal to a. Sum of a continuous and discontinuous function I claim will be discontinuous. Now to establish this, we would deploy what's called contradiction, right? fx plus gx, say, is phi x. I want to prove that phi x is discontinuous. Let me assume that it is continuous. Assume that it is continuous. Assume that it is continuous at x equal to a. Now, gx, which is discontinuous, then gx is discontinuous and fx is continuous. I am assuming that this is discontinuous, right? Now what do I get? I am assuming that it is continuous. I am assuming that it is continuous. Look at this then, gx, then, which is like a phi x minus fx, which is difference of two continuous functions, and therefore must be a continuous function, but gx is discontinuous. It leads to a contradiction, because gx is discontinuous, but it leads to being a continuous function. Therefore there must be some flaw with our assumption. Our assumption that phi x is continuous must be incorrect. Phi x therefore must be discontinuous. Phi x therefore must be discontinuous. So sum of a continuous and discontinuous function must be a discontinuous function, always. Sum of a continuous and discontinuous function must necessarily be a discontinuous function. Got me? So far so good? Suppose again, say fx continuous at x equal to a, and gx continuous at x equal to a. Then I claim that phi x, which is fx into gx, will be continuous at x equal to a. Phi x will be continuous at x equal to a. Easy to see. Limit phi x as x tends to a is limit fx as x tends to a into limit gx as x tends to a, or rather limit fx into gx as x tends to a. Now both these limits exist and are finite, so limit of the product will be product of the limits, because both the limits exist owing to continuity of fx and gx. Both limits exist at x equal to a and are finite, so limit of the product will be product of the limits. And because f is continuous at x equal to a, this is fa. Because gx is continuous at x equal to a, this is ga, which is phi a, which causes phi to be continuous at x equal to a, which causes phi to be continuous at x equal to a. So product of two continuous functions is a continuous function. But product of two discontinuous functions, let's examine that, right? Product of two continuous functions will be a continuous function. Let's look at product of two discontinuous functions. By and large, you would expect it to be discontinuous, but until and unless you come up with a situation where you find it to be continuous, right? Say for example, fx is plus 1 when x is greater than or equal to 0 and is minus 1 when x is less than 0. Do you realize it's discontinuous? Because limit fx, x tends to 0 from the greater than 0 side. From the greater than 0 side is 1. Right hand limit at x equal to 0 is 1. Limit fx, x tends to 0 from the less than 0 side. Less than 0 side is minus 1. So the left hand limit at 0 is minus 1. The right hand limit is 1. The function fx is discontinuous at x equal to 0. Right? Let me look at another function gx, which is, say, minus 1 when x is greater than or equal to 0 and is plus 1 when x is less than 0. Is gx discontinuous? Yes, the right hand limit at 0 is minus 1, left hand limit at 0 is plus 1. So gx is discontinuous at x equal to 0. So f and g are both discontinuous at x equal to 0, right? But look at their product, fx into gx. For x greater than or equal to 0, both are equal to, one is 1, the other one is minus 1. So is minus 1 for x greater than or equal to 0. And for x less than 0, minus 1 into plus 1, that's also minus 1. X less than 0, that means fx into gx is minus 1 for all x. Yes or no? Is therefore a continuous function. So product of two discontinuous functions, may be continuous as well as discontinuous, may be continuous as well as discontinuous. Yes or no? Clear? Right? Product of two continuous functions will always be continuous, but product of two discontinuous functions may be continuous as well as discontinuous. Product of a continuous and discontinuous function, right? By and large, you would expect it to be discontinuous, right? Until the time you give a counter example, right? So, say fx is x. It's continuous at x equal to 0. Fx equal to x is a function which is continuous at x equal to 0. Straight line y equal to x. Gx, say, is sine 1 by x when x is not 0 and is 0 when x is 0. This is discontinuous at x equal to 0 because limit sine 1 by x as x tends to 0 does not exist. It oscillates between minus 1 and plus 1. See, the nature of this discontinuity is like an oscillatory discontinuity. Oscillatory. Sine 1 by x as x is brought closer and closer to 0 just flutters between minus 1 and plus 1. It oscillates between minus 1 and plus 1. It's an oscillatory kind of discontinuity, right? So this is discontinuous at x equal to 0 even though it's defined at x equal to 0. It oscillates when you bring it closer and closer to 0. Sine 1 by x does not tend to a specific finite value. It just very vigorously oscillates between -1 and +1. Right? That's what it does. So gx is discontinuous at x equal to 0. But fx is continuous at x equal to 0. Right? Continuous at x equal to 0. This is discontinuous at x equal to 0. Right? So fx into gx. When x is 0, this will be, when x is not 0, this will be sine 1 by x, and this will be x. When x is not 0. Right? When x is not 0, it will be, I'm sorry, x sine 1 by x. It will be x sine 1 by x when x is not 0. Right? And will be x into 0 when x is 0. It will be 0 when x is 0 and will be x sine 1 by x when x is not 0. Right? This is the product of a continuous and a discontinuous function. This function is continuous at x equal to 0. This function is discontinuous at x equal to 0. But what is limit fx into gx as x tends to 0? 1 by x as x tends to 0. It's going to be 0. Because this is bounded. This will lie between -1 and +1. Whereas this tends to 0. So this will tend to 0. This will not be 1. Right? This will tend to 0. This will be a finite number always lying between -1 and +1. Therefore, this limit will be 0. So the limit at x equal to is 0. And the value of the function at x equal to 0 is also 0. So do you realize that fx into gx is continuous at x equal to 0? So the product of a continuous and discontinuous function may be continuous, may be discontinuous. Got me? Is that all right or not all right? Similarly, quotient of two continuous functions always be continuous provided the denominator does not become 0 at x equal to a. That means if f is continuous at x equal to a, that means is fa, and g is continuous at x equal to a, that means limit gx x tends to a is ga, then a function like fx by gx will be continuous at x equal to a provided ga is not 0. Because to be continuous at x equal to a, this must be defined, but if ga becomes 0, this will become undefined. So quotient of two continuous functions will be a continuous function provided at that point of consideration the denominator does not become 0. You want to independently examine quotient of a continuous and discontinuous function, quotient of two discontinuous functions you want to examine independently from all the inputs that I have given. Now let me state a few more facts. Can I wipe this off? Right. Can I wipe this off? See, I told you product of continuous functions will be a continuous function, right? Realize that x is continuous for all x. Y equal to fx is going to be continuous for all x. Right? Yes or no? So, x into x, product of two continuous functions will be a continuous function. Into x will be a continuous function. Into x, say r times, would be a continuous function, yes or no? So x per r will be continuous for all x. X per r will be continuous for all x, yes or no? Right? So lambda times, or say ar times x to power r will also be continuous for all x. If you multiply a continuous function with a constant, then the resulting function will be a continuous function, yes or no? Right? So which means if n is a positive integral index, then a naught x power n will be continuous. Sum of continuous functions will be a continuous function. So if I add a1 x power n minus 1, this will be a continuous function. Sum of two continuous functions. Sum of any number of continuous functions will be a continuous function. This is a polynomial of degree n. It therefore is continuous for all x. So a polynomial, a quadratic, a linear, a cubic will always be continuous for all real x, right? So polynomial functions will be continuous for all real x, right? Yes or no? Right? Trigonometric functions are also continuous for all members that belong to the domain of the function. Sin x will be continuous in its domain, cos x will be continuous in its domain. All trigonometric functions will be continuous in their respective domains, See, you might be tempted to say, hey, tan x is not continuous at x equal to pi by 2. Left hand limit at tan x at x equal to pi by 2 is plus infinity. Right hand limit at x equal to pi by 2 tan x is minus infinity. So it doesn't seem to be continuous at x equal to pi by 2. That's because x equal to pi by 2 is not belonging to the domain of tan x. Tan x is actually undefined at x equal to pi by 2. So tan x is x equal to pi by 2 is not a member of the domain of tan x. Will not be a member of the domain of tan x. Right? Got me? Logarithm log x, y equal to log x is continuous for all x. All x belonging to its domain. This is the graph of y equal to log x. As x tends to 0 from the greater than 0 side, it tends to minus infinity. This is the graph of y equal to log x. Hey, at x equal to 0, it's not defined. So x equal to 0 is not belonging to its domain. The domain of this is 0 to infinity is its domain. So for any x greater than 0, less than infinity, tan x is, log x is continuous. Log x is continuous. E power x will be continuous for all x. The graph of y equal to e power x is like this. It's continuous for all x. This is the graph of y as e power x. As x tends to minus infinity, y tends to 0. As x tends to plus infinity, y tends to plus infinity. That is what happens in e power x. Right? logarithmic, exponential, trigonometric are all continuous in their domain. Polynomials are continuous for all real values of x, because every real x is a member of the domain of a polynomial function, right? In fact, let me also tell you, say fx is defined from a to b to c to d, right? This is the domain of fx and this is the codomain of fx, right? Now if fx is invertible, that means it must be 1 to 1 as well as on to, right? That means now the codomain will coincide with the range. This is also the range of fx. Yes or no? Now let me state that if f is continuous in a to b, then this will be the domain, for f inverse. This will be the domain for f inverse. F inverse is then continuous in c to d, because these will be the inputs for f inverse, these will be the outputs for f inverse. F inverse, if it exists, will be continuous in the range of fx, which is c to d. F inverse will take values of x belonging to this interval, and in this interval the inverse would be continuous. Now a very important property of continuous functions. This is a function continuous in the interval a to b. This is fx continuous in a to b. This is a function fx continuous in the interval a to b. This is x equal to c, where the function assumes a value small a. Let's say this is x equal to d, where the function assumes a value capital M. Small m is the least value of the function in this interval, and capital M is the greatest value of the function in the interval. Yes or no? Fx is the smallest value of the function in the interval. Small m is the smallest value of the function in the interval. Capital M is the largest value of the function in the interval. So now this leads us to a property that a function which is continuous in an interval must necessarily have a smallest and a largest value in that interval. I'll tell you, you might think it's so obvious, but I'll tell you this is true only for continuous functions. For discontinuous functions, it may or may not be true, which is what I'm going to demonstrate. So just write down a continuous function, a function continuous in an interval, a function continuous in an interval must assume extreme values in that interval, that is having a minimum and a maximum. That is having a minimum small m and a maximum capital M. Minimum small m and a maximum capital M. This is the extreme value theorem. This is the extreme value theorem, also called Bolzano theorem. Bolzano theorem, extreme value theorem. Fx must lie. Fx will lie between small m and capital M. This is Bolzano's theorem. Extreme value property. It's called the extreme value property. And if fx lies between small m and capital M, that means we say fx is bounded. We say fx is bounded. A function continuous in an interval must necessarily be bounded. A function continuous in an interval must necessarily be bounded. Right? That means if its domain is bounded, its range, which is small m to capital M, will also be bounded. That's what it means. If the domain of a continuous function is bounded, its range will be bounded. Right? Bounded. Smallest value and largest values are the same. See, if a function is discontinuous in an interval, it may not have a smallest and largest value both. For example, say agreed, this is the smallest value of the function. And this is discontinuous. Let's say at x equal to c, it is discontinuous. Does it have a largest value? It's not bounded. A discontinuous function need not be bounded. A continuous function over a finite interval must be bounded. But see, this is a function discontinuous at x equal to c. You can perceive in the interval a to b the smallest value, for example, of this function. But can you tell me the greatest value of this function? There is no greatest value. There is no greatest value. This is not bounded. A continuous function will be bounded over a finite interval. A discontinuous function need not be bounded. Need not be bounded. Right? You can see it doesn't have a maximum. Right? The extreme value property fails for discontinuous functions. May fail. May fail. Not necessarily may fail. Right? And see, doesn't mean that a discontinuous function will necessarily not be bounded. May or may not be bounded. And in this case, it is not bounded. But I can have a discontinuous function which is also bounded. Say, for example, this is the point P. This is the smallest value of the function, and realize fa is the largest value of the function. Fa is the largest value of the function. So this is discontinuous in the interval, but it is bounded. Continuity would certainly mean it will have a smallest and largest, but discontinuity will have no implication. Whether it's bounded or not cannot be guaranteed in a discontinuous function. Right? Is that all right? Another mighty useful property for continuous functions. Mighty useful property for continuous functions. see this is a function continuous in an interval a to b. This is a function continuous in an interval a to b. This is a function continuous in the interval a to b, right? And it has a value small m, the smallest value of the function, and it has a greatest value, say capital M of the function, right? It has a smallest and a largest value. Fx lies between small m and capital M, right? Fx is bounded. Now think of any number between small m and capital M, right? Say L is any number that lies between small m and capital M. L is any number that lies between small m and capital M, right? Now draw a line y equal to L. This is a line y equal to L. L can be any number lying between small m and capital M. If you draw a line y equal to L, it will certainly intersect the graph of the function at least at one point, right? So y equal to L certainly intersects the graph of y equal to fx at least one point. Point say P. It could be at more than one point also, but it will intersect the graph at least one point, where L is any number lying between the smallest and the greatest value that the function assumes in that interval. Yes or no? Right? That means there exists at least one C. There exists at least one C in the interval for which the function assumes a value equal to L. Yes or no? That means there is Fc equals L. Yes or no? For any L lying between small and capital M, for any L lying between small m and capital M, there exists at least one C for which Fc is equal to L. And this is true for any L that lies between small m and capital M. That means at least one C exists. One C belonging to A to B must exist for which Fc becomes equal to L. That means if you think of any number L lying between small m and capital M, the function must assume for some value of x in the interval A to B that value L. This is what it means. Right? If small m is 1 and say capital M is 3, right? If small m is 1 and say capital M is 3, and you think of any number lying between 1 and 3, say if you think of a number 1.8 which lies between 1 and 3, there must be at least one value of x in the interval A to B for which the function assumes a value equal to 1.8. If you think of a number 2.8, there must be at least one x in the interval A to B for which the function assumes a value equal to 2.8. Any value intermediate between small m and capital M, the function must assume at least once in the interval A to B. All values lying between small m and capital M are assumed at least once in the interval A to B. Yes or no? right? Yes or no? Right? Does it make sense? In fact, not only that, not only that, not only that, so the function assumes all values between its smallest and largest, at least once. In fact, if a function is continuous in an interval a to b, say a function is continuous in an interval a to b, at x equal to a, it has a value fa. At x equal to b, it has a value fb. Right? If you think of any number L that lies between fa and fb, but if you think of any number L that lies between fa and fb, then there must be, and if you draw a line y equal to L, say, then it must intersect the graph at least one point. Yes or no? That means there must exist one value of c, at least one value of c in the interval a to b, for which fc is equal to L. Yes or no? Right? That means any L lying between fa and fb is assumed at least once by the function in the interval a to b. Right? Say if fa is 1 and fb is 4, and you think of any number between 1 and 4, the function must assume that value at least once in the interval a to b. That means if you think of a value 2.3, then y equal to 2.3 would be assumed for at least one value of x in the interval a to b. Right? If these are the values of the function, continuous function at the end points of the interval, then the function will assume all values that possibly lie between fa and fb, provided it is a continuous function. Provided it is a continuous function. Yes or no? Say, say fx is x minus a whole squared into x minus b whole squared plus x. Suppose fx is x minus a whole squared into x minus b whole squared plus x. Right? This is a polynomial continuous, this is a polynomial continuous, this is continuous. So fx is continuous everywhere, continuous for all x, right? And consider an interval a to b. Consider an interval a to b. I claim that there must exist one x, one c in the interval a to b, for which fc becomes a plus b by 2. I claim that there must exist at least one c in the interval a to b, for which fc is a plus b by 2. Very simple, because look at the value at the end points of the interval. fa is a, right? fb is b, and the number L actually lies between fa and fb. The number a plus b by 2 lies between fa and fb, must be lying between a and b, right? That means this function must assume this intermediate value which lies between fa and fb at least once. That means there must be at least one c for which the function becomes a plus b by 2. This property is called the intermediate value property for continuous functions. Intermediate value property of continuous functions. IVP, intermediate value property for continuous functions.
So in this case it is for A and B. In general it will be for the least and the largest value.
That also, and this is intermediate, means lying between extremes. That's lying between minimum and maximum. The idea is the same only. You want to nature call? Right then. So we just read what's referred to as the intermediate value property, right? If a function is continuous in the interval a to b, and at the end points it assumes values like fa and fb, then the function assumes all values between fa and fb. For any y equal to L, there must exist a C for which the function assumes a value equal to L. Right? That's the intermediate value property. So if fa is 3, fb is 4, the function will assume all possible values between 3 and 4 if it is continuous in the interval a to b. Now, clear? Say there is a function continuous in the interval a to b, function that is continuous in the interval a to b, and at the end points of the interval it assumes values that differ in signs. Fx continuous in a to b, such that at the end points of the interval it assumes values differing in signs. Fa into fb is less than 0. Fa into fb is less than 0, say. That means one of them positive, one of them negative. Now, in its attempt to do this, in order to go from negative values to positive values or from positive values to negative values, it has to cross the x-axis at least once, right? That means there must be at least one C. There must exist at least one C. One C belonging to A to B for which FC is 0. C therefore would be a root of the function. C therefore would be a root of the function. Root of fx equal to 0. So, if a function changes sign in an interval, if a continuous function changes sign in an interval, it must have at least one root in that interval. If a continuous function changes sign in an interval, it must at least have one root in that interval. Right? In fact, say if a function, continuous function changes sign in an interval a to b, it has to go from point A to B, right? It can either go like this with one root in the interval A to B, right? Or with three roots in the interval A to B, right? One, two, three, four, five roots in the interval A to B. In general, an odd number of real roots in the interval A to B. So write down a continuous function that changes sign in an interval, a continuous function that changes sign in an interval, must have an odd number of real roots in that interval, must have an odd number of real roots in that interval. That means a function, that continuous function that changes sign in an interval must have an odd number of real roots in that interval. It could have one real root or three real roots or 1, 2, 3, 4, 5. 5 real roots or 7, right? That is guaranteed. That means one real root for sure. It could be more. But then it can't be 2 real roots. It could be 3 real roots or 5 real roots or 7 real roots and so on and so forth. Now, you might be tempted to believe something like this. At x equal to a, x equal to b. Hey, you might be tempted to believe there are only 2 real roots. Yes, these are actually 2 coincident roots. So 2 plus 1, 3 real roots, right?
So the number of complex roots will be 0.
No, no. This does not tell you about the number of complex roots. All that it tells you is the number of real roots will be these many. There could be any number of complex roots. Complex roots can't, how can a complex number lie between 2 real numbers?
Real roots also can be after A and B.
Huh?
Real roots and also
Can be after A and B, yes. All that I am saying is a proposed interval A and B in which the function has changed sign, in that interval for sure it has at least one real root. This speaks nothing about the number of complex roots. This speaks nothing about the other roots that don't lie in the interval A to B. There is no mention of that in this statement, right? What is the nature of this discontinuity? Why? Now, if a continuous function didn't change sign in an interval, right? Say if I had a function that didn't change sign in an interval, see this, in this case, for example, it has no real roots in that interval, right? Or it could have had 2 real roots in that interval. Right? Or it could have had 4 real roots in that interval. See? Four real, 1, 2, 3, 4. In general, an even number of real roots. It could be 0, 2, 4, 6, etc. Right? A function, continuous function that didn't change sign in an interval must have an even number of real roots in that interval. It could be 0, or it could be 2, or it could be 4, it could be 6, and so on and so forth. Right? Yes or no? In fact, a very important consequence of this change of sign for a continuous function is the following. Can I wipe this off? See, if Px is a polynomial of an odd degree, if Px is a polynomial of an odd degree, call it a0 x power n plus a1 x power n minus 1 plus a2 x power n minus 2 plus an. N is odd. N is an odd number. Say a0 is positive. For definiteness, say a0 is positive. Now this I could have written as x power n a0 plus a1 by x plus a2 by x squared plus an by x power n. Right? Yes or no? Right? Now, as x tends to minus infinity, n is odd, by the way, n is odd. This is a polynomial of an odd degree, means n is odd. The highest power of x must be an odd number, right? As x tends to minus infinity, then these tend to 0. X to power n will tend to minus infinity because x is minus infinity, n is odd. So raise it to an odd power, it will maintain its sign. So minus infinity into a positive number would be minus infinity, and these will tend to 0. So Pnx tends to minus infinity as x tends to minus infinity, right? As x tends to plus infinity, these will tend to 0. This is a positive number, plus infinity to power n. Pnx will also tend to plus infinity, right? Right? So then if it's a polynomial of an odd degree, realize that suppose a is positive, as x is minus infinity, this is minus infinity going in this direction, that's plus infinity going in that direction. At x equal to minus infinity, the value of Pnx is rock bottom there, right? As x tends to plus infinity, the graph goes heavenwards there, right? That means the graph of this continuous function must go from this point to that point, from down there to up there, yes or no? In the process of going from here to there, do you realize that it must necessarily cross the x-axis at least once? It must necessarily cross the x-axis at least once. That means if it crosses the x-axis at least once, it must have at least one real root. It must have at least one real root. So write down every polynomial of an odd degree, every polynomial of an odd degree with real coefficients, every polynomial of an odd degree with real coefficients must have at least one real root. So where did you encounter a polynomial of an odd degree? Do you remember anything in odd degree? Not in quadratics, in parabola. See, feet of the normals drawn from a point hk, at cube plus t into 2a minus h minus k equal to 0. That was a polynomial of an odd degree. A cubic in t, and it always, I told you, has at least one real root. That means from any hk, at least one normal could be drawn to the parabola. I told you this, because this cubic will have at least one real root, right? T was the feet of the normal from hk to the so if there is at least one value of t causing at cube plus t into t 2a minus h minus k to be 0, that means at least one real normal from hk to the parabola, right? That's one place where we encountered a polynomial of an odd degree and where we dealt with it extensively, right? Yes or no? Now, suppose there is a function y equal to fx defined from domain is 0 to 1 and range is 0 to 1. So this is the domain of the function, and that's not just the codomain but also the range, which is, in this case, let's say for a specific function, let's say this is also the range of a function fx. Now I claim that there must exist at least one c belonging to 0 to 1, or entire thing, let's say inclusive of this, one c belonging to 0 to 1 for which fc is 0. fc is, say, 1 minus c. fc is 1 minus c. There must exist at least one c belonging to 0 to 1 for which fc is 1 minus c, where fx, let's say, is known to be a function continuous in its domain. Continuous in its domain. Fx is continuous in its domain. I claim that there must exist one c belonging to 0 to 1 for which fc is 1 minus c, right? Now, that means there must exist one c for which fc plus c minus 1 is 0. There must exist at least one c for which fc plus c minus 1 is 0. Let me construct a function phi x, which is fx plus x minus 1. Let me construct a function phi x which is fx plus x minus 1. Fx is continuous everywhere, x minus 1 is continuous everywhere, so phi x will be continuous everywhere, right? Now, phi 0. Let me examine phi x in the interval 0 to 1. I want to show that phi x has at least one root in the interval 0 to 1. If phi x changes sign in the interval 0 to 1, it must have at least one root in the interval 0 to 1. That's the objective, right? What is phi 0? Phi 0 is f0 minus 1. Hey, the range of the function is 0 to 1. That means the value of the function will always be less than or equal to 1. The value of the function will always be less than or equal to 1. That means f0 will always be less than or equal to 1. That means f0 minus 1 will always be less than or equal to 0. Yes or no? Because this is the range of the function. The function will always have a value which is always less than 1. That means f0 also will always be less than or equal to 1. Yes or no? Right? No, didn't understand this, no? Less than or equal to 0, sorry. f0 minus 1 will always be less than or equal to 0 because f0 will always be less than or equal to the upper limit of the range, right? Phi 1 is f1 plus 1 minus 1, right? Which is f1. But the function will always have a value which will always be greater than or equal to 0. So f1, which is what this is, will always be greater than or equal to 0. That means in the interval 0 to 1, phi x changes sign from negative to positive values. In the interval 0 to 1, phi x change sign, right? Phi x is continuous in the interval 0 to 1 and it has changed sign in the interval 0 to 1. That means there must exist an x belonging to 0 to 1 for which phi x is 0. There must exist an x belonging to 0 to 1 for which phi x is 0, right? That means for which fx plus x minus 1 is 0, there must exist an x in the interval 0 to 1. That means there must exist an x for which fx is 1 minus x. That means there must exist a c, that x you can replace by c. There must exist a c for which fc is 1 minus c. Yes or no? Right? Got me? Sometimes you can also deploy a graphical approach towards doing certain things. Say the same problem, you know, hey, this function y equal to fx, is only defined from x equal to 0 to x equal to 1. The values of y that the function will assume, this is y equal to 0 and this is y equal to 1. Right? The function x takes values only from 0 to 1, y takes values from 0 to 1 for this function. Yes or no? So the graph of this function is confined to this square. The graph of this function will be confined to this square, right? Now, think of a line y equal to 1 minus x. This is 1, 0. This is 0, 1. Think of a line y equal to 1 minus x. Do you realize y equal to 1 minus x means x plus y is 1? This is the line y equal to 1 minus x. Yes or no? X and y intercepts 1 both, right? This is the line y equal to 1 minus x, right? Now the graph of fx, at x equal to 0, fx will assume some value, say f0. At x equal to 1, say fx will assume some value, say f1. At x equal to 1, fx assumes a value f1. At x equal to 0, fx assumes a value, say f0. Now the graph of fx has to go from this point to this point. Yes or no? It is continuous and it has to go from this point to this point. Now if it has to go from this point to this point, do you realize it will intersect y equal to 1 minus x at least at one point p? Yes or no? Yes or no? Now, if this point is c, that means for x equal to c, what is y? 1 minus c. That means this length PC is 1 minus c. this length for x equal to c, this length is 1 minus c, yes or no? But 1 minus c, this is also fc. This is also the value of f at x equal to c. That means there exists a c for which fc is 1 minus c. There exists a c for which fc is 1 minus c. Got me?
Sir, why are we taking a line y equals to 1 minus s and not
Because I have this y equal to 1 minus c, so I look at y equal to 1 minus x. So I'm essentially looking at intersection of the two graphs, the intersection of y equal to fx and y equal to 1 minus x. If these two intersect at a certain value of x, that means for that value of x, fx will be equal to 1 minus x. That is why. Right? Say I have a function fx defined from in the interval 0 to 1 to R domain, and this is the codomain, right? And say for this, and it's continuous in this interval. And say f0 is f1. Say f0 is f1. I claim that there exists a C belonging to 0 to half. There exists a C belonging to 0 to half for which fc is fc plus half. For which fc is fc plus half. There exists a C belonging to 0 to half for which fc is fc plus half. Right? What I do is I construct a function which is fx minus fx plus half. I construct this function, let me call it phi x. In fact, zero to one only, 0 to half, yeah, 0 to half only, 0 to half only. All right. Now look at phi 0. What is phi 0? f0 minus f half. f0 minus f half. Yes or no? What is phi half? F half minus f1. Right? Yes or no? But f1 is the same as f0, that's given in the problem, right? So this is f half minus f0. Phi x is continuous in the interval 0 to half, and phi 0 and phi half are of opposite signs. Do you see that? This is f0 minus half, f half. This is f half minus f0. So phi x changes sign in the interval 0 to half. So phi x must become 0 somewhere in the interval 0 to half, right? Because phi x changes sign in the interval 0 to half. Phi x becomes 0 somewhere for x belonging to 0 to half. That means fx minus fx plus half is 0. For some x belonging to 0 to half, that means fx is fx plus half. That means there must exist a C for which fc is f of c plus half. Yes or no? Day 1 on continuity.